Anybody else need their exam? Let's grab yours out of there.
He's like, does this make any sense? He put use common sense, he put on.
Okay, so let's get started. A couple of things. We'll talk about the test at the end. I'll put up what the class did, the average, all that stuff. But we're going to continue with our series. Last time we met, I had to actually go back and look at the YouTube video to see what we talked about. But we had pretty much completed the geometric series. And in this section 8.2, there's still 2 other series that we haven't discussed. And so if you tried your homework, you probably had trouble with that. So let's get these other 2 taken care of. And then we will try to get into 8.3 today. I don't know if that'll happen. So also I want to point out that we are at a place right now in the class where, we're at that final stretch, right? We don't have a whole lot of time together. We don't have a whole lot of time left together. So, yeah, it's 3 weeks, but, it's going to go like that. So, that's 6 class meetings, and we have a lot of material to cover. So, my point is that a lot of you kind of are going to know at this point where you are in the class, what you need on the final to pass, to get a B, to get an A. And historically, what I've seen in a class like this, the exams are right there. Just be careful, don't hit my tripod on the way. Historically, what I've seen in a class like this is students are like in a pretty good position with their grades. So they kind of say, all right, well, I've got to study for this and this and this. So, I'll kind of ease up on the Cal 2. And, if I wind up taking a C, I take a C, whatever. And I understand that. It's your grade. But I think Chapter 8, the material here, is probably the most important in terms of people who are moving on, computer science, engineering, this whole idea of series. So try your best to stay focused. I know after Thanksgiving it's hard. We all go eat turkey and then it gets really difficult to focus on anything. So do your best to keep up with the homework, and your final exam is going to be mostly Chapter 8. It's almost completely Chapter 8. So, all right. So geometric series, we looked at those, and everyone has their little cheat sheets. Anyone need one? The one that has, anyone need this? Because I have a couple of copies. No? Okay. So if you look at this chart here, we have talked about the nth term, we've talked about geometric series, and that is it, right? Okay, so let's proceed with harmonic series. So a harmonic series is any series that has this form. Some constant over n. All right. Now, more importantly, and the thing I really want you to see here, is that you have a constant over a linear expression in n. So it's a linear expression in n. Like this isn't n squared, this isn't n cubed, it's not the square root of n, it's n to the first power, right? So we would say that's linear. So if you ever see a constant over some linear expression in n, then it qualifies as being a harmonic series. Now, the most basic example I can give you of a harmonic, here's an example of a harmonic, is this one. This is the classic harmonic series 1 over n. So let's first talk about what's the difference between this, something like this, and geometric.
It's not raised to the power.
Okay, good. So with geometric, just to remind you, geometric looks like a times r raised to the n minus 1. Notice that the n, the variable, the index, is up in the exponent. So this is almost like exponential function, whereas this is just some sort of like rational function with a linear expression in the bottom. So if you are looking at a series trying to figure out what it is, if n is not in a power, you can rule out geometric. All right? So we've got this. Let's go ahead and write out the first few pieces of this sum. So if we plug in 1, we get 1. Plug in 2, we get a half. Plug in 3, we get a third. Plug in 4, we get a fourth, and so on and so forth, right? So we want to know what this adds up to be. It's an infinite sum. Well, the first thing we could do is do the nth term test, right? So what would the nth term test tell us?
It diverges if the limit of n approaches infinity doesn't.
Yeah, so what we're doing is we're taking the limit of the sequence, which we're ignoring the sum, we're just looking at this, and we're taking the limit of that and seeing what it goes to. And that's a pretty obvious one, right? That goes to 0. And the nth term test, if you look off of that or if you remember, if it goes to 0, then the test is inconclusive. The test fails, in other words. So this tells us nothing, all right? So this test fails. So that test doesn't help. And the only other thing we have is geometric, right? That's the only other thing we've learned. So at this point, we're kind of stuck. All right, so I'm going to now show you what this series does. And hopefully I can convince you of this. This can be a little bit bumpy, but I think most students get what's about to happen. All right, so let's take a look at this example. I'm going to look at just this one specifically and see if I can convince you of something. So if we take the sum n equals 1 to infinity, 1 over n, we write that as 1 plus a half plus a third plus a fourth. I'm going to do a lot of these. Plus a fifth, plus a sixth, plus a seventh, plus an eighth, plus a ninth, plus a tenth. I'm going to go all the way out to 16. 11, 12, 13, 14, 15, 16, and plus dot, dot, dot. So it continues, right? That's what that sum is. We're trying to figure out what it is. All right, so here's what I'd like for us to do. I'd like for us to start combining some of these terms together. All right, so watch how I do this. I'm going to put, let's see here. I'm having a brain fart, but I think, yeah, let's put those two together right there. So what would that be if I combine those two together into one fraction? 7, so plus 1 plus a half plus, you said this is going to be 7/12. Do y'all agree? Get a common denominator? Okay. And then plus, and then if I put, now this is the tricky part. I don't want to put these two together. I want to put these 4 together. So we would need a common denominator, wouldn't we? Okay, so I don't want to go through that step of getting common denominators. So can we just put question mark for now? Okay, then I want to take the next 5, 6, 7, 8. Yeah, the next 8 of them. And I'm going to put those together, and that's going to be plus some question mark. You with me? Okay, now, do you agree with the next statement? The next statement, watch. This sum, okay, this sum, whatever it is bigger than the following sum. 1 plus a half plus, let me do it this way, 1/4 plus 1/4. I'm going to group those together. Plus, let's see, 1/8 plus 1/8 plus 1/8 plus 1/8. I'm going to group those together. I'll explain this once I get through it, okay? 1/16, 1/16, 1/16, 1/16. I need 8 of these. 1/16, 1/16, 1/16, 5, 6, 7. One more. 1/16 plus dot, dot, dot. So I'm going to group these together. So let's see if you can make sense out of this. I'm claiming that this sum, which is this with question marks, is bigger than, well, let's see. 1 is the same, right? Okay, a half is the same. Okay, so look at this 1/4 and 1/4. The way I did this was, you see how we had 1/3 and 1/4? Yeah. Okay, which one of those is smaller? 1/4 is smaller, right? So if I do 1/4 plus 1/4, that's going to be smaller than that piece. Agreed? And then if you look at this 1/5, 1/6, 1/7, 1/8, 1/8 is the smallest one. So what I did is I did 1, 2, 3, 4 of those 1/8. instead of 1/5 plus 1. Got it? And then over here with these 8 terms, 1/16 is the smallest. So I took 8 of those. You with me? Now, what are all of these sums? What is this, this, and this? It's 1/2, right? All of those. Look, that's equal to 1 plus 1/2. A fourth plus a fourth is 2/4, that's 1/2. An eighth plus an eighth plus an eighth plus an eighth is 4/8, that's 1/2. Plus a 16th plus a 16th, there's 8 of them, right? 8/16 is another half, right? So if I continued this pattern, I would take the next how many? 16 of them, right? And each one of them would be 1/32, right? 1/32. So I would take 16 1/32s and I would have another half. And couldn't you follow that pattern forever? Makes sense? So look at this right here. This right here, this sum is 1 plus the sum n equals 1 to infinity of 1/2. So look at this right here. This expression is just 1 plus 1/2 plus a half plus a half. See, n doesn't change, n has no effect on this, right? So it's just a half plus a half plus a half. And if you add that forever, what do you get? This should be infinite, right? Yeah. This diverges because you're just stacking 1/2 on top of 1/2 on top of 1/2. These pieces are not getting smaller, right? We need, in order for convergence, you have to have these pieces getting smaller. So if I did the nth term test on this, right? If I did the nth term, that would go to something that's not equal to 0, right? And so this one's going to diverge and become infinite. Does that make sense? And if this sum is infinite and this sum has to be bigger than that, y'all agreed with me that this is bigger, right? So that has to be bigger than infinity, and the only way you can be bigger than infinity is if you're infinity yourself. So that sum has to be infinite. Does that make sense? So it's just kind of a logical progression of this little clever substitution, I guess you could say, and you can conclude here that it's going to diverge. And therefore the conclusion is this: all harmonic series diverge. Okay, that's why it's not on your sheet. I don't know, well, I guess you could put it on here, but it's not on here because anytime you see a harmonic series, it's going to diverge. Anytime. Yes?
Okay, so I understand that they're all equal in half, but I don't get why we're allowed to make that substitution.
We're not making substitution. What we're doing is we're showing that this sum is logically bigger than this sum, right? Because that piece is bigger than that piece, and that piece is bigger than that piece. So if this sum becomes infinite, then this right here is saying that we've got this sum up here has to be bigger than that, which forces it to be infinite also. So we're not doing anything that's like,
Like a comparison.
it's like comparison, yes. I didn't want to say comparison because we actually do have something on here called the comparison test. So that's why I've not used that word intentionally. But yes, if you really want to look at it, what we're doing is we're comparing it to another series. And the series we're comparing it to is always smaller than the one we're looking at. And if this goes to infinity, then that one must go to infinity. Understand? Now, just since we're talking about this, what if our inequality was the other way around? I know it's not, but what if it was? And we concluded that this one here is infinite. Then what would it tell us about this one? Yes, so it would have to be smaller than infinity, but what would that mean? Would that mean it converges? It could still be infinite, because infinity is less than infinity, because infinity is an idea, right? So if this were flipped over, this actually would tell us nothing. So it's important that we were trying to find something that was smaller than what we were looking at, and that thing went to infinity. This is what the comparison test is going to be later.
What if it didn't converge?
If this had converged to a number, okay, so what if this thing had converged? What if this went, and then we said at the end of the day, this added up to be 10, let's just say. Then all we could say is that this is bigger than 10, right? Which means it could converge. Maybe it converges to 20, but it could also become infinite, because infinity is bigger than 10. So it would have told us nothing. Does that make sense? It's kind of like I have this series that blows up, right? This one right here, it blows up, becomes infinite, and then I have another series that's always above it. So it's got to go to infinity also. So if your series down here, this one, goes to a number, this one has to be bigger than it, could go to a number, or it could still become infinite. Does that make sense? Yeah.
So would we use something like this to kind of test a harmonic?
You don't need to test any harmonics. If you get a harmonic series on your homework or on a test, you just say it's harmonic, it diverges, and you move on.
And as long as it's a constant.
As long as it's a constant over a linear expression. That's right. So if you get something like this now, right, as another example, if you were to get sum n equals 1 to infinity of, let's say, 4 over n plus 1, that's harmonic. Okay, so you proceed, you move on. Okay, all harmonic series diverge. So that's it, we're done with harmonic. There's really nothing else to talk about with that. We will revisit some things with it. But now I need to add a couple of little notes up here before we tackle telescopic or collapsing. So make sure I get this in the right order here. Oh, where is it? Okay, here we go. So this is a theorem, and it says this. Suppose, I'll write the word out. Suppose you have two series Now, I'm not putting n equals 1 to infinity, but we're okay understanding that that's, okay, that's assumed. Anyone come in late, need their test still? Here we go. Anyone else? Okay, I'll bring it over there.
I already got it.
You got yours? Everyone's good over there? Okay. We'll talk about the test at the end. So let's say that we have two different series. Notice I'm using A sub n and B sub n. That means there are two different series, all right? Let's say that they both converge, and this is important. We're saying that they converge, not diverge. Then we have a couple of things. First of all, what is that saying? A constant times this piece, right, which is the sequence, a constant times the sequence doesn't change the convergence. It still converges. That's why, you know, when we were just doing the 1 over n, then if we did 4 over n, oh wait, hold on, scratch that. These diverge. I can't use this theorem, sorry. These have to converge. But basically the constant doesn't have an impact on the convergence. Geometric, yeah, the geometric, right? The geometric has that A out there, so that A doesn't have an impact on the convergence. What has the impact for the geometric is the R, right? Okay, so that's true, and then this one is true also. Sum of A sub n plus B sub n is equal to the sum A sub n plus the sum of B sub n. So this property, the second one, is the one that's going to be the important one for us right now, and that is, if you have two convergent series, then this adds up to be a number, right? And this adds up to be a number. So when they add up together, you get some number. And then, but that's the same as putting the sequences together into one series. So basically, you can pull apart and put together convergent series. You cannot do it with divergent, though, right? Only with convergent series, as you're about to see, all right? See, that's it. Oh, and also this could be a minus under here, and then a minus here. So it doesn't matter if you add or subtract. Yes?
That constant, the C,
Yes.
does it change the number? It converts
It does change what it converges to, but it doesn't change the fact that it converges. So remember, when we say convergence, or something converges, we don't necessarily know what it converges to. Now with a geometric series we do, don't we? If a geometric series converges, it goes to a over 1 minus r. Yes?
I'm sorry, I was stretching.
Okay. All right. So now let's talk about telescopic or collapsing. So this is our third, of the common series, this is our third one. All right, here we go. So I'm going to give you an example of one. Sum n equals 1 to infinity of 1 over n squared minus 2n. I need to change something real quick. I need to start this series at 3. Can anybody tell me why? If I plug in 2 for n, I'm going to get division by 0. Do y'all see that? So I start this series at 3. That's not a big deal. I mean, it's still an infinite series, right? It's just where I'm starting changed. Okay. All right, so let's see. Is this geometric? Should we run the nth term test first? Let's do the nth term. Take the limit as n goes to infinity of the sequence itself. And I think this is obvious. This goes to 0, right? Which tells us nothing. Fails. So we move on. Is it geometric? Do you see n up in a power? No. Okay. Is it harmonic? No. It's not linear, right? The denominator is quadratic. And so therefore it is not harmonic. So really the only thing left, at least in our book right now, is telescopic and collapsing. So somehow this is going to become telescopic. So here's what we're going to do. We're going to first recognize that this sequence inside factors, the denominator factors, right? And just for the sake of doing this, I would like for us to write out what the first few pieces of this would be. Like if we plugged in 3, what would we get? 1 over, let's see, 3 times 1, so that's going to be 1/3. And then plus 1 over 4 times 2, right? Which is 8, plus 1 over 5 times 3, which would be 15. We'll do one more, 1 over 6 times 4, which would be 1 over 24, plus dot, 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 right? So notice that by rewriting this sum, writing out the pieces, right? It's a positive number, right? Positive number, plus a positive number, plus a positive number, plus a positive number. So we're adding a bunch of positive numbers on top of one another, right? Does it converge? Does it diverge? We don't know. It could do either one right now. So you'll see why I'm trying to stress this to you, that it's positive plus positive plus positive when I do the next step. Okay? So here's my next step. Let's just step away from that for a second and go back to the good old days. So what am I doing here? I'm going to do partial fraction decomposition on that. Just like we did when we were integrating, right? This helped us in integration. This might help us here. Let's just see what happens. So I had 2 distinct linear factors. So I rewrite it as a constant over the first linear factor, constant over the second linear factor, and then I go try and find A and B, right? So we've done this enough, I hope, that you kind of remember what to do here. You clear the fractions out, and then you go try and get A and B. So, yes?
Do we drop, like, kind of like when we're doing partial fraction with integrals, do we drop the integral sign or do we drop that sign whenever we do the partial fraction?
Yeah, this is like, I'm doing this like scratch work. I don't know if that's what you mean.
Yeah.
Yeah, I'm doing this like scratch work.
Okay.
Yeah, this is separate from this thought right now. I'm going to say, hey, can I break this down? So I'm going to try. So let's see if we can get a. To get a, I let n be 0. So if n is 0, what happens? What do we get? 1 equals negative 2a. So a is negative 1/2. That's what a is. Now how do I get b? Let n equal 2. Okay, so if n is 2, we get 1 equals, now this is gone, right? And we get 2b. So b is 1/2. Right? Okay. So now, that means this is negative 1/2, and that's positive 1/2, right? All right, I'm going to rewrite the series now. Come back over here. I'm going to say that the sum n equals 3 to infinity of 1 over n squared minus 2n is equal to the sum n equals 3 to infinity of negative 1/2 over n and then plus positive 1/2 over n minus 2. Do y'all see how I did that? I'm just rewriting this. We factor that, do partial fraction decomposition, we get this. I'm going to do another step here. This is equal to 1/2 times the sum n equals 3 to infinity, and then we have minus 1 over n plus 1 over n minus 2. So what did I do there? Yeah, I took out 1/2 here, right? And brought it out of the sum. Now, if you know what, earlier I put the properties on the board and I said that this converged. Remember I said that if the sequence or the series converges, then this will also converge. Go back in your notes and just add this to it. Just add that. You can pull the constant out. I haven't formally said that, but if this is a convergent series, then you can pull any constant out of the series.
Only on convergent?
Only on convergent. Yeah, so just add that into the theorem that I put up there. Okay, so that's what I've done here, right? I pulled out a common factor out of these two, brought it out here, and then brought that out of the series to out here. Now, this is a little tricky. What is this? Like by itself, what would that be? What type of series is that? It's harmonic, right? And then by itself, that one right there is also harmonic, right? So you could claim that this is going to diverge. Here's the problem, though, is that you know how, like you might be tempted, don't write this down, you might be tempted to write this. But you can't. Because these are divergent, right? And that property allowing you to split things apart only works for convergent series. And so we still don't know what's happening here, right? So you're not allowed to do this. Therefore, well, let's just start writing things out, okay? Watch. This is 1/2. It's 1/2, right? And then this is going to be like something plus something plus something, right? Forever. So I'm going to put a bracket, and let's just start putting the sum in here. So what would happen if I replace n with 3? What's the first thing that I would get here? I'm going to do it in parentheses. Negative 1/3 plus 1 over 1. Agreed? That's what I would get if I plugged in 3. Now plug in 4. So plus negative 1/4 plus 1/2. That? Okay. Plus negative 1/5 plus 1/3. I'm going to keep going. Negative 1/6 plus 1/4. I'm going to go one more. Negative 1/7 plus 1/5 plus ... right? That keeps going. And then also I need to close the bracket. That ... dot's inside the bracket because the 1/2 would distribute to everything, right? Anybody see it? Remember in this sum up here, I said it was a positive plus a positive plus a positive forever? But if we rewrite it this way using partial fractions, what have we generated in here? Negatives, right? Minuses. And do you see any of them that kill each other off? Take a look at this 1/3. Doesn't that cancel out with that positive 1/3? Right? And then this negative 1/4, doesn't it cancel out with this 1/4? And then the negative 1/5, doesn't that cancel out with the 1/5 here? Y'all see that? There's a pattern to this, isn't there, in the way things are canceling. Does anybody not see that? What about this negative 1/6? Would it cancel? Eventually, right? So I've gone dot, 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 but we realized that the next one right here would be negative 1/8 plus 1/6, which would cancel out this 1/6, right? So I'm going to put an arrow into the dots. That negative 1/6 is canceling out with something in those dots, right? Would this negative 1/7 cancel out? Yes, that would cancel out with something in those dots. Agree? So let's see, what's left? What's still here? We have a 1, and we have a 1/2, and then nothing else. Well, what about this one?
No, it cancels.
Oh, I forgot to put it. Okay, I'm sorry. Forgot to put the cancel. Okay, and then this, what? I forgot to, okay, I'm sorry about that. Okay, so the only thing I have left is the 1 and the 1/2, right? But we need to think about this a little bit more. As you move down this series, right? In order for this negative guy right here to cancel, you have to be able to go 2 down, right? So even though a lot of stuff's going to cancel, as you move out, you constantly are trying to like catch the next one to cancel. I don't know if that makes sense. So we are not done, okay? We have not shown anything yet. What we are doing right now is establishing a pattern, okay? So I'm going to write down on the board, like in words, what the pattern is. And this is going to seem kind of weird when I write this. First guys killed off by second guys two groups down. Okay, let's see if that makes any sense to you. Does that make sense to you or not? If we're looking at these parentheses as groups, okay, these are groups, then the first guy in a group, right, the first guy inside of a group is always killed off by the second guy in the group, but 2 groups down. Does that kind of make sense? Okay? It's a weird way of saying it. Well, how would you say it? Yeah. Pardon? It could turn out that in a different series, it may turn out that the second guy gets killed off by the first guy 5 down. So you have to establish the pattern first, all right? First guy in this, any first guy in a group, right? Look at this first guy, right? He's in a group, first guy gets killed off by the second guy 2 groups down. So I go 1 group down, 2 group down, the second guy there kills him off, right? Now, are we okay? It's 2018, so am I okay using guys? Yes? You sure? Okay, I mean, I'm being serious. If anyone doesn't feel like I'm inclusive enough, we can do different things as we move on. I'm gonna get in trouble. It's coming. I'm gonna get in trouble. I'm recording this. I may not post this lecture. Hey, it's your generation, not mine. All right. Okay, here we go. So how do we do this? I mean, I think we've established that a lot of things are canceling, right? A lot of stuff's canceling. But we constantly have this tail piece that's kind of like moving out and then gets killed off, but it still moves out forever. So how do we establish what this sum is doing? We have to recall, this is from previous notes, that if a series converges to what we called capital S. So whenever we have a convergent series, we always said, okay, it's converging to this thing capital S. If this is true, then that means this. The limit as n goes to infinity of S sub n equals S. Now, does anybody remember what this is? It's not. It's a sequence. This is the nth, what we call the nth partial sum. So you might remember when we first started series, I said, hey, look, remember sequences were just a bunch of list of numbers? And then the series created a new sequence, which was the sums. So we had like S sub 1 was the first one. S sub 2 was the first 2 added up, 2. S sub 3 was the first 3 added up, right, of the sequence. And then keep on going down, right? So S sub n is the first n added up. And so if we want to know what's happening, if the sum converges, then that limit of the partial sums must go to S. Okay, now how am I going to use that? Here's what I'm going to do. I'm going to take a look at this series. Okay, now that I've established the pattern, first guys get killed off by second guys 2 groups down. Okay, I've got that kind of burned into my brain now. What I'm going to do is I'm going to write down what S sub n is. So what is S sub n? What is the nth partial sum? So what I want to do is I want to start going out here, but I actually want to stop instead of going forever. And that would be S sub n. And then I'm going to take the limit as n goes to infinity once I'm done. Okay, so here we go. Let's write out the nth partial sum. So it's the same as this sum, right? It's the exact same thing, except I don't do dot, dot, dot at the end. So I'm going to go kind of small here. 1/3 plus 1 plus negative 1/4 plus 1/2 plus negative 1/5 plus 1/3. And I'm going to go enough of these that I can kind of reestablish that pattern. I think that should be good. So that gives me like at least two of the cancelings, right? Are there. And then plus, and instead of saying dot, 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 watch, I've left myself plenty of room, haven't I? I'm actually going to stop this sum. Okay? I'm going to stop it by plugging n in at the very end. So I've erased the formula, but remember that this was the sum. No, it wasn't negative. It was negative 1 over n plus 1 over n minus 2, right? So if I go and I say, okay, plug in 3, plug in 4, and I say stop at n, I know it's weird to have the same letter here, but wouldn't the last one be, the last one would be negative 1 over n plus 1 over n minus 2? That's what would happen if I plug n in to the formula. That'll be the last one. Now, I have to look at what's happening in front of it, and you'll see why in a second. So what would be the one right in front of that one? Yeah, so I'm not plugging in n, I'm plugging in n, take away 1, so n minus 1 is getting plugged in. So this is negative 1 over n minus 1 plus 1 over, not n minus 2, n minus 3, because I'm doing 1 less than that, so n minus 3. Now, how many do you think I'm going to need to go back here? At least 2, right? Because that will establish the canceling pattern. Because we know the pattern is that you need 2 groups down to cancel. So I should get a canceling in this group. And let's see if we do. This one right here would be negative 1 over n minus 2 plus 1 over n minus 4, right? And I don't quite have enough room. I'll squeeze it. Okay, I'm going to force one more in here. Dot, 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 plus I'm going to force one more of these in here. There'd be negative 1 over n minus 3 plus 1 over n minus 5, right? And do you see my little dot dots in the middle? Which means that there's a bunch of crap in the middle of that, right? Okay, let's now go through and reestablish the pattern. First guys get killed off by second guys, 2 groups down. First guy gets killed off by second guy, 2 groups down. First guy gets killed off by second guy, 2 groups down. First guy gets killed off by second guy up in here somewhere, right? First guy gets killed off by second guy somewhere in there, right? So we know that this is still here and this is still here. Those two did not go away. Now think about it this way. These guys, they're obviously guys, are second guys, right?
Yeah.
Second guys get killed off by first guys, 2 groups. Which way? That way, right? So when I was saying first guys get killed off by second guys, 2 groups down, then second guys get killed off by first guys, 2 groups up, right? So that one doesn't go away because there is no first guy up there, right? This guy doesn't go away because there's no first guy up there. You're going to see it happen down here though. So let's start at the end here. This is a second guy. Second guys and first guys kill each other off, right? But second guys will be killed off by first guys 2 groups up. So it's the opposite. So this guy should get killed off. I should be able to go 2 groups up. So here's 1 group, 2 group, and it should be the first guy that kills him off. Do you see it does? What about this one? This is a what? This is a first guy, right? First guys get killed off by second guys 2 groups down. There's no 2 groups down anymore, right? This guy stays. He does not get killed off. He survives the onslaught here, okay? Then, what about this one? This is a second guy. The only way he's getting killed off is if there's a first guy 2 groups up. And there is. Right? This is a first guy. First guys get killed off by second guys 2 groups down. There is no 2 groups down. He stays. Okay? Second guy gets killed off by first guy 2 groups up. Is there? Yes, somewhere, right? Somewhere in that ... that one's going to go. And then this is another second guy that gets killed off by first guys 2 groups up. So somewhere in here. Again. And so what I have underlined in black is the only thing left in this sum. Right? Everything else has gone away. So S sub n is actually just 1 plus a half and then plus negative 1 over n minus 2, or no, sorry, n minus 1, and then plus negative 1 over n. Yes?
Put the 1/2 on the outside.
Oh, yes, thank you. I forgot. S sub n, let me back this up. S sub n equals 1/2 times this. Yeah, thank you for pointing that out. Okay, we good? Now, why do you think they call this a collapsing sum? Yeah, it's kind of like, when I think of it, and there's no like right or wrong to this, I think about like a bridge going across a river or something like that. And you know, the bridge collapses and all you're left with are the 2 supports at either end, right? Everything else just kind of collapsed out. And that's what happened here. You had some stuff at the front, you had some stuff at the back, and everything in the middle just fell out. Make sense? Now we're not done, we have to take the limit of that. Okay? We have to take the limit of that. But I also want to just make sure you understand the wording. So we understand collapsing? Why do they also call it telescopic? This one's a little weirder. Yeah, it's those old school telescopes, you know, that are like, they get smaller and smaller like that. And then when you kind of like do that and pull it apart and look, and then when you're done, you push it back together and put it away. So when you push it back together, you just get that end and that end really together, right? Everything in the middle goes away. So you'll hear both terms, all right? So now, S, the true sum of this series is the limit as n goes to infinity of S sub n. That's the definition. So what is the limit as n goes to infinity of that? So 1/2, 1 plus a half, plus negative 1 over n minus 1, plus negative 1 over n. It's pretty simple limit here, right? That goes to 0 and that goes to 0 if n goes to infinity. So these vanish. So yes, they did wind up not mattering, okay? So you get 1 plus a half, which is 3 halves, times 1/2, so you get 3/4. Okay? So if we kind of summarize, that's it for telescopic, okay? I mean, that's obviously we had to do a little bit of work, right? We have 3 common series: geometric, harmonic, and telescopic. Of these series, one of them automatically diverges, right? This is divergent. Now, with the remaining 2, geometric, we've seen it can diverge, right? If the absolute value of r is bigger than or equal to 1, this diverges. If the absolute value of r is less than 1, it converges. So with geometric, if it converges, can you actually tell me what it adds up to be? If it converges? Yes, it's a over 1 minus r, right? So geometric, if it converges, I'm going to put a check mark here. If it converges, we actually know the sum, right? We will actually be able to find s. We will know it, right? That's s. We know what s is if it converges. With telescopic, it's the same as geometric. It could diverge and it could converge. The only way to know if a telescopic actually converges or diverges is you must do this. You have to do s sub n, and you have to run the limit of that s sub n. Do you hear what I just said? Because you know how we established that pattern in the very beginning and we didn't do all this, we just had dot, dot, dot? If you would have just said, hey, these 2 are left, you would have got the same answer, correct? But that would have been luck, because it is possible that the terms down here that are left can diverge. It is possible to have a series that's telescopic, but these guys, when you take their limit, go to infinity. And then it would diverge. Now, there's an example of that in the homework, all right? So you'll see that. But the point is this: with telescopic, you must do this. The biggest error I see on the test is that people will just establish the pattern and assume that the crap at the end just goes away and just give me this as the answer. And if you do that without doing s sub n, then you'll get major points taken off. So telescopic, you're going to establish the pattern, use partial fractions or something else. You'll see in the homework there's problems that have logs in them, where you have to do some properties of logs. You know how logs you can like turn division to subtraction, right? That you'll see it in the homework. So, but you have to run through this s sub n step, all right? All right, so these 2 series, telescopic and geometric, are the only 2 series that we are going to deal with in this class. The only 2 that we can actually find the sums of if they converge. Every other series that we look at, all we will be able to say is it converges or diverges. Now, so why am I stressing this? Because on a test, if I give you a problem, like number 1 on the test, let's say, and I say this: find the sum. And then I give you some series. What is the hint that I have given you there? It's either geometric or telescopic. Because the only thing you can ever find the sum of in this class is going to be geometric or telescopic. So if I tell you to find the sum, I'm telling you it's one of the 2. Now if I tell you instead, does this converge or diverge, then it could be anything. It could be these, but it could be a bunch of other things also, all right? So this is a big hint to you. Find the sum is a big hint. It narrows it down to 2 different possibilities. Yes?
If you just ask if it converges and it is telescopic or geometric, do you want us to find the sum?
You would have to prove to me that it is convergent, which means that you're going to wind up having to get that sum anyway. So if you show it to me, great, but I don't see how you can conclude that it would do something without getting the sum. You know what I mean? Like it has to happen. The work has to be done. All right, that's it. Now, is telescopic on your little cheat sheet there? No, it's not. Because this cheat sheet is a cheat sheet of tests that we run on series to see whether or not they're convergent or divergent. A telescopic series, when you write it all out like we just did, is not a test. We're just algebraically writing out the sum, right? That's what we're doing. Then taking a limit. So it's not here. Now we do need to talk about a p-series. And to talk about p-series, we actually have to get into the next topic, which is, we're still in, no, we're in 8.3 now. Okay, we're moving on to 8.3. While we're here, why don't we take a look at that series we just did? That telescopic one. It was 1 over n squared minus 2n? Okay. Now I need to cheat with my computer here because it's going to start at n equals 1, and that's going to cause a problem. So hold on, let me see where in my code I do this. Where the hell? Where's n? Where the heck is it? Well, I'm going to cheat. Just don't pay attention to this. No, that's not it. I'll show you something while you're sitting there, because we're going to need this later. Here's the problem. Check this out. Yeah, yes, I would, because we're going to do this later, all right? So this is going to come up later on, that right now this series starts at n equals 3, right? I would like you to rewrite this series so that it starts at n equals 1 instead. Okay, so how would we do that? How would we actually turn this into a series that starts at n equals 1 instead of n equals 3? So here's the idea. What I'm going to try and do is make that 3 become a 1, right? So what I need to do is subtract 2 from it, right, to make it a 1. So imagine if this equation, instead of saying n equals 3, said n plus 2 equals 3. Do you see that equation? Then I could subtract 2 from both sides and get the 1 on the right side. Yes? So what I need to do is everywhere in the problem, I'm going to replace n with n plus 2. So for this series, replace n with n plus 2. So what would happen if I do that? If I replace that with n plus 2, then I get that equation, right? Which I can solve for n and get 1. So this would become this now, right? And then I would have 1 over, and then this would be n plus 2 squared, because I'm replacing n with n plus 2, and then minus 2 times n plus 2. This series, if you were to start and plug in 1, then 2, then 3, start writing out the pieces, would be exactly the same as this one. They'd be exactly the same. Do we have to convince ourselves of that, or do you believe it? Yes? Okay, just plug in 1 real quick. Plug in 1, what would you get here? 3 squared, 9. 3, right, so 3 here, 5. I'm sorry, 1. What am I doing? 1 is 3, so 3, 6. So 9 minus 6, you get 1/3, wouldn't you? That would be the first piece. Now over here, what do we get if we plug in 3? 9 minus 6, so this is 1/3 also. So what we've done is we've adjusted our index. Do y'all see that? I've shifted my index from 3 to 1. The reason why we need to do this later is because we're going to have multiple series. We're going to be trying to combine them into one series, but some of them are going to start at 3, the others are going to start at 2, and maybe the other one will start at 4, and we need to get them all starting at the same place, and then we can put them together.
So we can go backwards and see the, like, see that one, we can go to the.
Yeah, if you wanted to go here and take this back here, then you need to make that a 3, right? So to make that a 3, I need to add 2 to it. So I need to write, and minus 2 is 1. See, to make that a 3, so I can add 2 to both sides to make it a 3. So I replace all my n's with n minus 2's. So I place that with n minus 2, that with n minus 2, and you will indeed go back to this. We'll have more practice with that. The reason why I'm telling you this, though, is because my computer program right now, the way I have it written, it starts at n equals 1 all the time. So I need to do this real quick shift. So I need to put that in the computer, and I thought I did. N plus 2 squared. Oh, okay, yeah, this is right. I had typed it in right. The problem was I hadn't gone out far enough. I was trying to figure out what it converged to. Did y'all see what it's converging to? Looks like 0.75, right? Our answer was 3/4, wasn't it? So you can see that that series appears by the computer to be converging to what we said it would converge to. All right. So now 8.3, integral test and comparison test. We'll do these one at a time. Yeah, this one's good. So the integral test. When you see integral test, you should be thinking, oh, I'm going to have to integrate, right? I mean, it's in here, right? So I'll start this out with, let's take a, yeah, you know what? I'll use a computer. So that way I don't have to draw it out for you. Let's look at a sequence, not a series. Let's look at a sequence. Let's look at 1 over n again. This was harmonic, right? That's a harmonic sequence, or a harmonic series, I should say. But that's the actual list of the points. All right. So this right here, we know it diverges, right? We know it diverges. So if I were to go to each of these and back this up just a little bit. Let's go first 10 points, maybe a little easier for us to see this. Okay, so my first point right here is at 1, right? So I go 1. When I plug in 1, I get 1. I'm going to draw a rectangle that comes over here like this. Okay? Now at 2, it's 1/2. And I'm going to draw a rectangle that goes like this. And then at 3, it's 1/3. And I'm going to draw a rectangle that goes like that. So that's 1 unit high, 1/2, 1/3. Yes? This one's 1/4. And this keeps going. You get the idea? Okay. All right. Now, if I were to draw the function 1 over n, right? That's the function f of x equals 1 over x, right? Because it's nice and continuous and curved like that. You see that? So is there a relationship between the integral of this? Now remember, the integral of this is the area underneath it, right? Is there a relationship between that and the sum of the red things? So this red block is bigger than that, like it goes above that graph, right? And so it looks like, I guess what I'm trying to get you to see is that the way I have it drawn, I can't really set up a good relationship between